Greetings, everyone, and welcome to All the Math. That's all the math you need for computer science. This is volume 2 of our series on linear algebra, and together we're going to be taking a journey through the world of vectors and matrices and the operations on them and all that they can be applied to and solve. It's going to be a fascinating journey, and I hope you're excited about it. I know I am. If you've taken volume 1 of All the Math, welcome back. If you haven't, that's okay. Nothing in this volume is going to be depending on the previous one as any kind of a prerequisite. There will be a few ideas that come up again in a different context, but I'm going to make sure that I explain all those from scratch so that you're not required to have taken the first volume in order to take this one. This is going to be a very applied and theoretical course. I'm going to be trying to sort of strike a balance between the two. Not only are we going to be talking about the algebra and about the formulas and the symbols used to describe the linear algebra world of matrices, we're also going to be doing some programming in your choice of programming language, either R or Python, which are both modern programming languages that support all the linear algebra operations we're going to need. Basically, at the end of each episode, I'm going to have a couple segments, one on R and one on Python, in which you're going to put some of these ideas to practical use. I want to make sure this is a very applied class, and that it doesn't just come out you knowing a bunch of kind of abstract things about what a matrix is, but not really understanding how to do them in the wilds, down in the trenches, and not understanding how the applications of them work. Because really, that's what makes linear algebra so powerful, is that especially in our modern computing age, we are able to leverage our computing resources to do a lot of operations on large matrices and come up with some fascinating results. Now, I will tell you right off the bat that this linear algebra stuff is some of the coolest math that I have ever encountered. It is elegant, it is beautiful, some of the results are breathtaking. It doesn't seem that way at first. When you first learn what a matrix is, you learn it's kind of this spreadsheety type thing with rows and columns in it. And you learn how to get certain rows out and certain columns out and what the dimensions of it are. And you're kind of like, whatever, that's just, pretty easy. It doesn't seem like there's much there. Then you learn about linear transformations from one dimension to another, and you learn about the rank nullity theorem and how orthogonal matrices operate and how you can decompose a matrix into its QR decomposition or into its eigenspectrum and learn about what the eigenvectors and eigenvalues mean and how they unpack all the deep hidden properties of the matrix. Oh my gosh, it is amazing. And it gives you this deep insight into sort of how numbers and the relationship between numbers work. I still, to this day, seriously cry when I think of eigenvalues. Like, real tears cry. They're that beautiful and that special. And when you learn sort of how they relate to the matrix as a whole, I think you'll find them as breathtaking as I do. And you'll have a totally new appreciation for math and how it can apply to practical problems. All right? I'm getting ahead of myself, though. All I want to do in this opening episode is two things. First of all, I want to sort of break down the title of the subject, linear algebra. We're going to talk about each of those two words. And then I'm going to do a little segment on the applications just to sort of give you a bird's eye view of some of the amazing things that linear algebra is applied to and can solve, many of which will surprise you. They won't seem like they're vector or matrix things at all. Information retrieval, Google, graphics, these things aren't going to seem like they have anything to do with matrices, and yet you will discover that the reason that the technology that we take for granted every day can be used is largely because of the stuff that we're going to learn about in this volume. All right, so first let's take the title. So linear algebra is the name of the discipline. Let's take the second word first. Now when you first hear that, you might say, algebra? I took algebra in 8th or 9th grade or something, right? I was kind of hard at the time, but I've sort of mastered how to factor an equation and all that kind of stuff, right? Why am I having to take this again? So here's what you got to understand. The word algebra with a capital A, as we often use it, refers to a particular, simple, as it's taught in middle school, field of math that has to do with using variables to represent different values, right? And you learn the principles of how those go together and how you can use the quadratic formula to solve a quadratic equation and all that kind of stuff, right? That is algebra with a capital A. Now, mathematicians will talk about an algebra as sort of a more general thing with a lowercase a, and an algebra can be thought of essentially as a system of mathematical objects that obey certain properties. Okay? So it's sort of a general notion. You can talk about an algebra that uses numbers and variables that represent numbers, and that is the algebra that you learn perhaps in 8th or 9th grade or whatever, right? One of the key ideas of an algebra, by the way, is the idea of closure. and we're going to talk about the elements in an algebra being closed under certain operations, right? So if you think about what you did in algebra, you learned that you could take 3 divided by 4 plus 5 times 4 minus 9, all that divided by 3, all that divided by 6 or something, right? And of course, you could also represent things with letters, x minus y times z minus 5 all over x plus z squared. Now, one important thing to understand that you take for granted until you realize that it could be different. The reason that this expression and this one have any real meaning is because each of these operations, like division and addition and multiplication and subtraction and division again, each of those operations is closed in that algebra, meaning when you take 2 numbers and you add them together, you get another number, which you can then subtract from another number to get another number, which you could then multiply a number to get another number, which you could then divide by a number to get another number. Whenever you take 2 numbers and perform an operation on them, you always get a number back. You never take 2 numbers and add them together and get a fish, right? You never take a number divided by another number and get a pocket knife or a system of government, right? You always get back another number. And because you always get back another number, that's how you know that an expression like this can have meaning. Because 3 divided by 4, maybe that's hard and it turns out to be a fraction and a decimal and I can't figure that out in my head. But whatever it is, I know it's going to be a number. And I know, therefore, I can add it to another number. And whatever that turns out to be, I'm not sure, but I know it's going to be a number, which I can therefore multiply by this thing. And what's this thing going to be? It's going to be another number, because 4 minus 9, whatever that is going to be another number. Numbers, you always get back numbers, okay? So that's sort of a common property of algebras, and the one we're going to be covering in this volume is the algebra of matrices. We're going to be talking about a matrix. It's going to be very simple at first, but as I said, that conceals a lot of deep, profound complexity that we're going to get into. But the bottom line is that when you take 2 matrices and do something with them, like add them or subtract them, or take the dot product or the norm, there's all these different things we're going to talk about, you're going to get back something in the same set, something of the same kind. You're going to get back another matrix, which allows you to build up matrices in complex algebraic expressions. And so that's really what we mean when we talk about linear algebra. We mean the same kind of algebra, but instead of dealing with numbers, we're dealing with matrices, which is a different kind of mathematical object, right? Now, the first word I want to spend a little bit more time on, the word linear. You may have encountered this word before. You probably encountered it in algebra that you took in 8th or 9th grade. It's a word that's used colloquially today to talk about various things. For instance, I heard someone talk about Memento, which is one of the films from Christopher Nolan that you may have seen. He's the guy who did Inception and the more recent Batman series with Batman the Dark Knight. People talked about that as a non-linear movie, right? And when they talked about it as a non-linear film, what they meant was, as you're watching the movie, the scenes didn't unfold in order, right? In Memento, you had to sort of realize, wow, we're doing like flashbacks and flash forwards all the time. It's told not in a sequence that you're typically used to seeing. And some people called that a non-linear script. Kind of interesting. I actually really enjoyed that movie, by the way. Linear is a word that comes from the word line, right? And it essentially means that there is a relationship between 2 things that goes as a line. There's a famous a quote that's attributed to Stanislav Ulam, who's one of the guys who worked on the Manhattan Project, developing the atomic bomb with John von Neumann and others in the 30s. And this phrase is interesting to him. He said, dividing the world of functions into linear and nonlinear is kind of like dividing the world of zoology into elephant and non-elephant. That's what he said. Okay, so, and what he meant by that was, well, you can take all the animals at the zoo and you can divide them into the elephants and the non-elephants. Sure, that's a valid partition in the All the Math Volume 1 sense. But it's kind of misleading, right? Because it's not like you've evenly partitioned them at all. And there's a heck of a lot more numbers of beasts and a lot more diversity in the non-elephant class than there is in the elephant class, right? The class of elephants is really a very strange, particular, special case of all the animals. And so he's saying, there's tons and tons of different kinds of functions in the world. Isolating the linear ones turns out to be kind of a weird thing to do, okay? So that is true, and Stanislav Ulam is not something someone I would ever argue with. But there's a sense in which it really is important to single out linear ones as bona fide special case. And here's why. A couple reasons. Number one is there are certain things that really do behave linearly and which we take for granted and are used to dealing with linearly every day and simply wouldn't make sense if they're not linear. Okay? The second reason is because if it's linear, it gives us certain nice properties that we're able to take advantage of, and we're able to do some amazing math that really would break down as soon as we're dealing with a nonlinear case. All right? So I'm going to take the first one here. So the definition of linear essentially is this. You know, we're used to this idea where we have a function, right? And this is the input of the function, and what we get back from the function is an output. And what we mean when we say we have a linear function is these two things. What we mean is we say, well, if we have f of some constant times x, well, that's just going to be the same as that constant times f of x. So in other words, if we're taking f of something times a variable, really that factor, that constant factor, can simply be factored out and be used to multiply by the thing itself. So all we need to do is figure out what f of x is, and then we know what f of ax is for any value of a, because we can simply perform this multiplication outside of the function. The other thing it means is this. If I want to know what f of x plus y is, if it's linear, that's the same as just taking f of x plus f of y. And you may be able to see here that because of these two rules, this allows me to very easily divide and recombine complex problems. If I'm dealing with f of a bunch of stuff in here, and maybe that bunch of stuff is a bunch of stuff plus a bunch more stuff plus a bunch more stuff, well, I can simply break down each one of these into individual pieces and deal with it, and then just add back up the results, because all I need to do to take all this complicated stuff plus some more complicated stuff is figure out each piece individually and add them up here, right? Now, there are certain things, like I said, where of course it's linear and it's just going to be, and it seems really weird if it's not. So let me give you an example. Suppose you go down to 7-Eleven or Wawa or whatever, and you want to go in and you want to buy a candy bar, right? And you want to get one of those big, Hershey Special Darks. That's one of my favorites, right? So you take a candy bar and you go up to the cash register and you say, hey, I'd like to buy this. How much is it? And the cashier looks at it and says, oh, okay, that candy bar, that'll be $2, please. You're like, wow, $2, that's actually not too bad for one of those big giant candy bars. You say, I'm going to buy them for the whole family. I'm going to go ahead and get 5 today. I'll get 5 candy bars. So you put them on the counter and you get ready to get out your wallet. And you get out your $10 bill, you're ready to pay them. And the cashier says, 5 candy bars. That'll be 25 cents, please. Now, that would be really strange. I think you'd agree, right? You're like, wait a minute, what, 25 cents? I was going to buy 1 candy bar. It was going to cost $2. Now I decided to buy 5 candy bars because that was a good price. That ought to cost $10, right? It ought to be linear. If I have 5 times as many candy bars, it ought to cost 5 times as much money. And really what we're doing when we say that is we're drawing attention to this equation. We're assuming that if I have the cost of 5 candy bars, that of course ought to be equal to 5 times the cost of 1 candy bar. And that's because it ought to be, according to our intuition and our societal norms, ought to be a linear relation, right? A linear function. When I then go back to him and say, geez, if you're charging me 25 cents for 5 of these, man, I'm going to go get all the ones you can. So you go back to the thing and you clear out the shelf and you go through and you bring 17 candy bars there and you put them up on the shelf. And you say, I'd like to buy all 17 of these, right? And the guy says, 17 candy bars, great. That'll be $1 million, right? And you're like, wow, $1 million for 17 candy bars. Again, this cashier, who's a little bit loco, is imposing a non-linearity on you, right? And he is violating that common sense principle, which is you buy a certain number of candy bars, the cost ought to be that number times the cost of 1 candy bar, right? And the second equation on that page is really the same. When we look at this equation here, what we're really saying is, you know what? If I want to know the cost of buying 2 candy bars today plus 3 more candy bars tomorrow, well, that ought to be the cost of 2 candy bars plus the cost of 3 candy bars, which, using our first red expression here, we can further break down to say 2 times the cost of 1 candy bar plus 3 times the cost of 1 candy bar, right? Which, of course, all boils down to 5 times the cost of 1 candy bar. This sort of math is easy to work with. It's easy to intuitively figure out. It's easy to take a complex expression and just radically reduce it to something simple. And we're used to dealing with this every day, again, because many of the things that we deal with in life are, in fact, linear and wouldn't make sense otherwise. Now, maybe I overstated that because, of course, there are non-linearities with candy bars, right? Maybe the store is saying, hey, buy 4, get 1 free. As soon as they say that, they've actually made it not a linear function, right? And now buying 2 candy bars and then 3 isn't the same as buying 5 together, right? Because if you bought 5 together, well, guess what? You're going to get one of those free. Whereas if you bought 2 one day and 3 another, you wouldn't get 1 free. And so that relationship would break down. But there's clearly many things in life that actually deal with linear relationships. Think about driving in your car, right? If you're going to drive from Fredericksburg, which is where I live, up to D.C., it takes about an hour. Then maybe you want to go north to Baltimore. That's going to take another hour, maybe hour and a half to get from D.C. to Baltimore. Now, it goes without saying that going from Fredericksburg to Baltimore would take 2 or 2.5 hours, right? It'd be really weird if it took an hour to get to D.C. and then another hour and a half to get to Baltimore. But to get from here all the way to Baltimore took 10 hours or took 10 minutes, right? That wouldn't make any sense because we know that distances follow that linear relationship here, right? If I work during the day for a certain hourly wage, maybe I make $10 an hour, it would be really weird if I said, let me work 5 hours at $10 an hour, and then I work 5 more hours the next day, and I simply couldn't add up my total pay, but instead it was this weird formula that didn't go proportional to the number of hours I worked at all. That's yet another example of something that we assume is going to be linear. Let me give you an example of something that's not linear, though. It's also very common, right? So suppose somebody told you, hey, I really want to know, let me not do weight, let me do height. It's a little bit easier to get your head around. What if I wanted to know what the height of the average 10-year-old was? Well, is that going to be 10 times the height of the average 1-year-old? I would say probably not. Is that going to be equal to the height of a 9-year-old plus the height of a 1-year-old? I would say probably not. Is it going to be the height of a 5-year-old plus the height of a 2-year-old plus the height of a 3-year-old? You kind of put this into perspective and visualize the heights of those various people on average, you quickly realize that's not going to be the case. And that's why, if you're ever kind of wondering in your life, wow, I have this child, and this child is 2 years old, and they're just getting ready to start to walk, and they're about this high, gee, I wonder how tall they're eventually going to be. I wonder how tall they're going to be when they're 20. You certainly wouldn't multiply their height by 10, right? You wouldn't multiply their 2-year-old height by 10 and assume, they're 2 feet tall at age 2, they're probably going to be 20 feet tall at age 20. Well, obviously you're not going to do that. But that's because you know deep inside your mind that that's not a linear function. And therefore you don't take it for granted that those 2 rules apply. You know that you're not going to be able to apply them because it's simply a nonlinear function, right? So that's what linear and algebra mean. One more thing about that linear thing is how it relates to line, right? So again, if I make a graph here, and this graph is going to be something like the number of candy bars I buy on this axis, and this is how many dollars it's going to cost on this axis. Well, we basically said, 1 candy bar costs $2. If we're dealing with a sane store and not this kind of crazy one, then 2 ought to cost us $4. And 3 ought to cost us $6. And so if we make this line like this, that is the relationship between candy bars and cost. It's a straight line. Now, if somebody wanted to say, you buy 4 and you get 1 free, then that would mean that this went up to here and then cut straight over, right? And that would be a non-linearity. Because I would say, well, guess what? It's $8 for 4 of them. But at that point, you might as well buy a 5th one because that's going to be free. Okay? But without that sort of sale, that's why we get this thing, which is called a linear function. And again, that is obviously related to the word line because this thing is a line, right? And of course, if you looked at the age of a child and you looked at their average height of somebody that age, it's clearly not going to be a line, right? It's clearly going to look something like, maybe like that. where eventually you get to a point at age 18 where they've stopped growing, and the average 18-year-old's height is about the same as the average 58-year-old person's height. And actually, I've heard, although I haven't experienced it yet, that as people get a little older, they actually start to shrink a little bit, so you might see this thing going down. That's an example of a nonlinear function, right? So all the stuff we're going to be dealing with in linear algebra in this volume is going to assume that linear property. And that may seem very limiting, and in a way it is, but it turns out there's a whole lot of amazing stuff that we can unpack once we make that assumption, because all the math gives us some fabulous, elegant results that allow us to compute a lot of amazing things very easily.